Today we are talking about the topic of instability in tension. That is a material science, manufacturing science, instability in tension. So what is derivation? After that, we first of all discuss theory. So friends, once ultimate tensile strength is reached, the specimen will begin to neck and thus deformation is no longer uniform. This phenomena has important significance because non-uniform deformation will cause part thickness variation and localization in processing of material, particularly in sheet forming operations where the material are subjected to tension. Friends, in this topic we show that true strain at onset of necking is numerically equal to the strain hardening exponent n. Friends, you know that the slope of the load elongation curve at UTS ultimate tensile strength is 0. You see here dp equals to 0 at ultimate tensile strength UTS. Okay, it means friend the stability here instability is begins, that is the specimen begin to neck and can't support the load because cross sectional area of the necking region is becoming smaller as the test progresses. So friend, the relation you see here is we are establish some relations here. Friends, this is a true strain of epsilon. From previous derivation you got this ln equals to L naught divided by L. This is the original area divided by final area. So this is a logarithmic true strain. Here we establish this from previous data. So friends, if ln is here, then e to the power epsilon a naught divided by a. If you multiply cross, then you got this. This is got a naught, a equals to a naught into e to the power minus epsilon ne. So this is the first equation of this. This is the first equation. Friends, stress equals to force divided by area, or you can say force equals to stress multiply area. Okay, and force equals to stress multiply, from this first equation you put this value a multiply e to the power minus epsilon. Okay, so this is a final according to from one equations. After calculating you got dp equals to d epsilon equals to sigma into, in simple bracket you got, after calculation you got these values, and at UTS ultimate tensile strength dp equals to 0. So what dp upon d equals to here 0 divided by de equals to a naught d sigma divided by d epsilon e to the power minus epsilon minus sigma e to the power minus epsilon. Okay, here this will become 0. So what a naught, after calculation this will become 0, so this is also 0, and if you common e to the power epsilon, then this will also 0. So what d sigma upon de epsilon equals to sigma. This is the second equation. Friends, one more thing, sigma equals to k epsilon to the power n, where n equals to strain hardening exponent and k equals to strength coefficient. Okay, so we got some other numericals here. We know from second equation this value is find out, and also we know this sigma equals to this. So where sigma we put this value, after got, friends, after calculation of this value we find out this n equals to true strain. That means strain hardening exponent equals to true strain. This is a geometric softening. Friend, this equation is so that instability in tension test can be viewed as a phenomena in which two competing processes are taking place simultaneously. As the load on the specimen is increased, okay, its cross section area is decreased, okay, which become more pronounced in the region where necking is begin. In necking region, strain is increased where area is decreased. With increasing strain, however, the material becomes stronger due to strain hardening. Since the load on the specimen is produced of area and strength, instability sets in when the rate of decrease in cross section area is greater than the rate of increase in strength. So this phenomena is known as geometric softening. So this derivation is all about this instability in tension. So thank you.